Before I introduce our panelists, I wanted to just share a little personal and professional anecdote. This was a really meaningful and special moment for myself, but also for the organization I run, Fulcrum Arts. About 11 years ago, I was invited to take a job in Pasadena and help this small organization think through what could an art and science organization be. And one of the first things that I was able to do was build a residency program now called the Fulcrum Incubator. And the first artists I got to work with in that program were Evelina Domnitch and Dmitry Gelfand, who you'll be meeting in a minute, and who are the artists who created the video that you saw. It's actually a documentation of an artwork called Orbihedron. And by collaborating with another curator, Isabel DeSena, we were able to bring Evelina and Dmitry to LIGO at Caltech right after they had detected gravitational waves and won several Nobel Prizes. And through that process, I was also able to meet and begin conversations with this absolutely brilliant person, Rana Adhikari. And that early experience really informed how I would think about how can art and science work together in a way that's really meaningful and generative and dynamic and really allows us to think through some of these bigger, almost existential scientific questions. And it's just been my honor to have this moment tonight to tell these three wonderful individuals like how much their friendship and camaraderie has meant to me and has been able to help us build this really incredible program. Orbihedron is one of the works that came out of Evelina and Dmitry's residency, their conversations with Rana Adhikari. And it's now the first exhibition that we're hosting in our brand new space in Pasadena. It'll be up through January 19th. So if you want to see that absolutely crazy thing that you saw actually happening in front of you in real time, please come to our space so you can see it. You'll also hear a sound piece that accompanies it. That's part of what you heard today was by William Basinski's is actually a soundtrack that's included in the piece. So, you know, if many of you were wondering what would it be like to step into that world that Basinski and Evelina and Dmitry created, we have that for you in Pasadena. So please come. And you know, to these three individuals and Billy, of course, I'm very grateful to have had the opportunity to work with all of you and to bring you back to Southern California. So I want to talk a little bit about who these folks are, do a little bio. Evelina Domnitch and Dmitry Gelfand create multisensory installations and performances that merge physics, chemistry, and computer science with uncanny philosophical practices. Investigating questions of perception and perpetuity, their artworks exist as ever-transforming phenomena offered for observation. Because these exotic physical phenomena take place directly in front of the observer without being intermediated, they serve to vastly extend the sensory threshold. The immediacy of the experience allows the observer to transcend the illusory distinction between scientific discovery and perceptual expansion. So yeah, and in 2016, we partnered with Isabel DeSena to bring Evelina and Dmitry to conduct a 6-week research residency at the LIGO lab at Caltech as part of our inaugural Fulcrum Incubator residency program. It was at this time where the artists met Rana X Adhikari, a professor of physics at Caltech. He's much more than a professor of physics, as you will soon learn. Adhikari works on the experimental physics of gravitational wave detection and is among the scientists responsible for the US-based Laser Interferometer Gravitational Wave Observatory, which is LIGO, that discovered gravitational waves in 2015. He, along with Lisa Barsotti and Matt Evans from MIT, received the New Horizons in Physics Prize in 2019. for research on current and future Earth-based gravitational wave detectors. His research focus is on the areas of precision measurement related to surpassing fundamental physical limits to discover new phenomena related to gravity, quantum mechanics, and the true nature of space-time. So please welcome Rana Adhikari, Evelina Domnitch, and Dmitry Gelfand to the stage. But to kind of get things going, and Rana, this is probably a question you get asked a lot by family at Thanksgiving. And remember, this is, and I know you are so wonderful explaining these complex ideas to a wide audience. So could you explain what gravitational waves are, and what is the significance of that moment when they were detected at LIGO?
I was thinking about it while watching this, and I thought, maybe I think it's something else now. I have a different answer than I would have given you an hour ago, I think. And it's, we say gravitational waves, I think, because it feels a bit more familiar. It has that word gravity in it. And it's because we don't want to spook you with how spooky it is. And that's my new pitch I'm going to give you today. You haven't heard it before. I think what's really happening is a gravitational wave is a wave of definition, sort of, that travels throughout the universe. And it changes as it passes through you. It changes the distance between objects, and it changes the rate at which time flows. And so we're used to using these definitions of this is the number of dimensions in space and time we have. And that thing that we use, that's the bedrock of how we talk about things, that's the thing that changes when a gravitational wave comes through. And it's really a space-time wave, but we use the gravity word, for whatever reason, in the 20th century. And it is super weak. All of these things are so weak, which is the reason why you don't feel it all the time while you're just walking around on the Earth. But if you were in the neighborhood of what we just saw, you'd feel it. It would be like the gravity on your feet would be 10 times stronger than the gravity on your head. Or it would be that kind of thing if you were standing close to a black hole when it did its, whatever that was, that you just saw. And it's an extreme thing. But by the time it gets to the Earth, it's so weak that no one thought you could detect it. Einstein himself said, nah. I mean, it was a long paper, but it meant nah. And it just went on and on like that until a crazy person in the 50s who didn't understand how things worked said, yeah, I can do that. And then it took 50 years of improving upon that first crazy idea. And when we found it, we said, that's a mind-blowing thing, that the universe is quaking in itself. And that's a thing that we can now listen to. And it was a big deal when it happened because it took 50 years. But now they come in every few days. And so you can come around and listen to these space-time quakes if you want.
So is it correct to say that the LIGO detectors were able to detect the change of shape of our planet?
Yeah, they could.
Yeah.
But anybody could do that. We're a lot better than that. We could detect something like the change of the size of the whole planet by 1/10 of a millimeter. And that would be a pretty loud signal, I would say.
What was the kind of measurement of that initial detection at the time?
I don't know how to say it in regular words. You just imagine the smallest thing you've ever heard about, and it's about 1 trillion times smaller than that. And that's how much the Earth moved by when this wave first came through. And it was,
I can say.
Yeah.
What you gave me.
Tell me.
Did you hear the clicks in my piece at the end mostly, and some at the beginning? A few years ago, pretty much right after you LIGO geniuses discovered the gravitational waves and captured them, and I was at Cal Arts? For a lecture of Dmitry and Evelina, and if you've never seen them lecture, you must. Anyway, there was cocktails afterwards, and I met Rana. and Jamie, who's here, these two brilliant scientists. And Jamie came up and talked to me and said, you know, he was a fan, and would I like to do something with, they have recordings. And I said, oh yeah, I'm down. So they sent me these files. You've never seen waveforms like this. I don't know, I know there's like, you know, Ableton people out here and stuff, but I never saw anything like that before, even from Richard Chartier, okay? And and some of it was, well, I don't know what it was, but you know, you guys had to adjust the frequencies quite a bit just to be able to hear it, right? So I got some stuff from them, and Dmitry and Evelina wanted me to, you know, create a soundtrack for the installation, which is beautiful, which we showed. The video tonight is of their installation at Fulcrum, which you should go see because it's really spectacular to see the piece and their work. Anyway, so I created you know, I tried to go by the science and create this piece for Dmitry and Evelina, and they're like, but Billy, we want you. And I'm like, oh, I wanted to, you know, do the science. They're like, no. So I was like, okay. So I got creative, and I imagined that, you know, this is two fucking black holes creating a rift in space-time, okay, with their massive attraction and love for each other. 3 billion light years ago or whatever. So I had to imagine these waves traveling through space-time. And then, you know, in the second half of the piece, this is the long version. The second half, it gets very romantic. So that was, you know, when they come to Earth and everything. Anyway, that's my spiel.
No, that's right, man. It's like Kurt Vonnegut and Einstein.
Thank you. So I want to turn the question over to Evelina and Dmitry. You know, being able to be with you while you were conducting the research and documenting that as part of our residency was a real privilege, and I learned quite a bit. I would love to just hear from you, like, the process, because I think when we first had you come, I had very different ideas of what you would be doing. And suddenly you were telling me about dinner plates at the swimming pool. And I was like, what are they doing at a swimming pool with dinner plates? So I would love for you to sort of share how your research when you came to LIGO evolved. Because I do recall you mentioned you went to a specific lecture that just kind of ignited this whole new kind of way of thinking about you know, your work. And I was wondering if you might want to kind of share with how you arrived at LIGO to suddenly we're seeing these kind of hydrodynamic analogs of black holes.
Oh, this 6 weeks at LIGO, I can talk exactly 6 weeks, 24 hours a day about this incredible tension and almost telepathy that you have when you talk to scientists. We did a few residencies with scientists, and here, not only we had the pleasure of talking to Rana and Jamie, who are senior scientists, we were assigned 5 graduate students with whom we had conversations on general relativity and the kind of calculations they do in simulations of supernova explosions and the dynamic of star evolutions and lives of stars. So it was an incredible experience, and black holes being the threshold of knowing, which was The Limits of Knowing, the title of the exhibition where you premiered the big piece that became later On Time, Out of Time. Yes, you approach these limits of perception, of knowing, and you can do anything. You can look in any direction, because no matter what you fantasize about black holes, Rana thinks about it again and he has new ideas. It's this whirlwind of, where time stops, freezes.
It's very difficult to verbalize, but I think a nice point of departure brings to mind the penetrating words of theoretical physicist, cosmologist, and philosopher John Archibald Wheeler. Space can be crumpled like paper into an infinitesimal dot. Time can be extinguished like a blown-out flame, and the laws of physics, which we regard as sacred, immutable, are anything but.
But of course, we don't only mystify our audience. We like to bring physical experiences that are connected to our senses, because we're artists and we don't have to write papers and work out the math. So we wanted to bring it to the experience of the body and the mind. And the three things that are very important about black holes, where this concept originates, are space-time and gravitation. And space-times are so iffy, although you said it's vibrations of space-time gravitational waves, but do space-time really exist, or is it just structures of our consciousness? That's still a very long conversation, but gravity is something that we are so embedded in, and we experience it every moment, and it is so local. So we as artists, we're always interested in the opposite threshold of gravity, which is floating in space without mass, masslessness, levitation, and this is how all bodies in space are. And we have a bunch of works on the topic of levitations. We presented them. It's sound performances where we levitate very small objects on acoustic standing waves, and you can experience zero gravity. And I cannot even start imagining, 10G, or even the 10G, it's just like on a planet, but gravity on a star, it's impossible to imagine. And the work of Billy, this piece of music that he wrote, for me, it's really about floating in space without any gravity, like an ascendance where you keep floating, and you like in this infinite process of losing weight and going into this weightlessness. But yes, so between these poles of, weightlessness, it seems so natural, so easy to experience, but the other pole is so unimaginable. And the true experience, physical experience of these kind of events in space, at the end we decided to look into vortices. And a few lectures that we attended on theoretical physics and string theory, there is always mentioned in a little footnote this fluid dynamics analogs, the fact that certain phenomena that are very fundamental, they repeat on different scales. So not only on microscopic scale or on a scale of a galaxy or cosmological scale, but also on our human scale. And that's a kind of a vortex, a black hole that we have spun into existence at Fulcrum Arts. So everything we say about it it's, yeah, it doesn't have, yeah, it's poetry, but you should come and see the piece, and everyone will hopefully experience their own threshold.
Could you would you mind explaining kind of technically what's happening and how you arrived that you could actually make this work? And while Billy was performing, I was wondering, did they just shoot lasers at things until something cool happens? Like, how did you arrive at that understanding of how these things would behave?
Well, actually, it was the idea that you can create an analog of black hole is it's not all that new. It began in the 1970s. Theorist called William Unruh decided that a vortex is the way in which a liquid is twisted. It goes through this corkscrew around a singularity at the bottom of the vortex, around this area that becomes extremely thin, as some might even regard one-dimensional at the bottom of the vortex, that this is very, very close to the way that space-time gets distorted around a black hole. And when you send waves, be it sound waves or other kinds of vibrations near a black hole, they can get swallowed, and perhaps they might never become recognizable again, as the case of the so-called black hole information paradox. Can information indeed disappear and never resurface? This is the kind of questioning that led to all kinds of controversies in the domain of quantum information and the nature of black holes. And yet, as seemingly inaccessible as these domains might seem, you can conduct experiments, be it with liquids, be it purely with light. You can also do it with Bose-Einstein condensates. You can create very, very similar parameters with just a single vortex, or actually with several vortices. As we have a sister artwork that was also created, inspired indeed, as Robert had hinted earlier, by one of the lectures that we had the fortune of attending at Caltech by Juan Maldacena, who decided that, along with Leonard Susskind, I must add, that a wormhole connecting two black holes, and black holes, at least all of the ones that have been detected thus far, come in pairs. A wormhole is a manifestation of quantum entanglement. So what that means is that everything that is entangled, every particle that can be entangled with another particle that is on the other side of the cosmos, or simply inside of our bodies, or wherever it might be, constitutes a wormhole. And so to create that analog, indeed, we conducted experiments at the Caltech swimming pool. We very politely asked everyone to leave the pool because their vibrations would have an effect on our experiment. And yeah, we indeed, this is where it wasn't a dish, but rather a frisbee, and it can be done by other means. You can create a vortex pair. You can see these vortex pairs with the proper angle of light in any moving body of water. These it's a kind of a double eddy that is created. And so in the sister installation, we have about 1,000 liters of water and this vortex pair that hovers through the basin, and it is also lit by a laser, but from below, and you see the projection above you magnified significantly. Whereas in the piece that we're showing at Fulcrum Arts in Orbihedron, the laser beam is going directly into the dimple of this vortex, going straight through the singularity, and that creates a black hole shadow right below the vortex, around which, as you had seen in this video documentation, this constantly whirling halo of light.
Thank you. So I know we don't have much time left, so I'd like to bring this back to Rana. So
I just want to say a political statement.
Okay.
I think this is a lot cooler. Now that I'm looking at it, it's a lot cooler than it was when I first saw it. And well, it's because it's not just an analogy. I think it's such a cool thing to, if you're into this, what is the physics of the inside of black holes? This is a super cool idea that basically these days you know about things like pressure and temperature and other things that you learn about in high school. But all of those things, when you look at it deeply, it's a bunch of atoms bouncing around and things like that. But we have all these everyday words for it, like, oh, it feels hot. But it's really the atoms are vibrating, whatever's going on. And this thing of looking at gravity as if it's a fluid is probably really the best way to understand relativity, if you really wanted to. That relativity to reality is the way temperature or pressure is. It's just a thing that we have basic words for because we're primitive, hairless monkeys. And if we were smarter, we would understand what are the atoms of space and why is it that Einstein's rules are the way that they are. But we're not there yet. But this thing, it kind of, it's not scientifically precise or something like that, but it gives you the right feeling about what's possible. That if you take lasers and shoot it at things, cool things happen. And the same way, you learn about molecules, because if you shoot a laser or you put light through glass, it splits into a rainbow. And that tells you about what's happening microscopically. And this kind of thing, the idea that you could look at a shadow of a black hole and figure out what's really going on in the crust, I think it's not I don't know how to say it in this audience, it's not just art, but it might be like, that's the real truth. And I think for me, that was the power. This was the first time we had artists sitting in a science lab. I mean, people were asking me, what is going on? Have you just lost control of your people? And I said, I don't know what's going on, but let's just roll the dice and see how this goes.
Did they meet them?
Yeah.
Beforehand?
No.
Yeah, but then they're like, oh,
Yeah.
okay.
And for everybody, it was such a great experience because it makes you think about questions that you would just never do it because you're just stuck in your daily rut of doing your equations and whatever. But you don't need equations to discover new things about nature. You just got to have some creative people around talking about stuff and doing things. That's my political statement.
Yeah, so I was going to close and ask you a question to talk about the role of art in science, and because I know because of PST, the Gettys really look to you to kind of say these really beautiful things, but I think you kind of just said it.
Nailed it.
So I think, thank you all for coming. Would love for you to see the piece in person. I'm sure all the artists would appreciate that as well. And thank you for sticking around for this talk, and you can mob them after we get off the stage and ask them more questions. All right, thank you for coming.